In my previous video, I have seen the Wronskian. I have seen in my previous video how by Wronskian we can easily find a set of function be linearly independent or dependent. Also, how we use Wronskian to find the solution which is linearly dependent or independent in differential equation. Today I will see elaborately this concept. Actually today I will see some properties of Wronskian. Some theorem about this Wronskian. Suppose y1t and y2t be two solutions of the second order differential equation y double dash plus pt plus y dash plus qt y equal to 0, where pt and qt obviously set of continuous function on the interval I. Then for this second order differential equation, if y1 and y2 be the solution of this differential equation, then either Wronskian of y1 y2 is identically 0, means either the solution y1 y2 are linearly dependent, or Wronskian of y1 y2 are never 0. That means this solution would be linearly independent. That means the solution of second order differential equation either linearly dependent or linearly independent. And how we have to find this Wronskian, I have defined in my previous video. So at first I will highly recommend you, if you don't see my previous video, at first see my previous video. Then today's video would be so easy. And second, if Wronskian of y1 y2 not equal to 0, that means y equal to c1 y1 plus c2 y1 is the general solution. And the solution y1 y2 are also called fundamental set of solution. For any initial condition y t not equal to y naught and y prime t not equal to y bar naught, for this initial condition I will always get unique c1 c2 such that given differential equation has a unique solution. Okay, this property is very important, and now I will prove this property. And the proof is such type, such second order differential equation. Here, since the initial condition is y t not equal to y naught and y prime t not equal to y bar naught, for this second order differential equation, since c1 y1 and c2 y2 be the general solution, now put this initial condition in this equation, then I will get y c1 y1 t naught plus c2 y2 t naught equal to y naught, and c1 y prime 1 t naught plus c2 y2 prime t naught equal to y bar naught. And obviously this is look like non-homogeneous system of linear equations, so we can write this as matrix from, and A would Ax equal, this is look like Ax equal to B, and the A would be y1 t naught, y2 t naught, y1 prime t naught, y2 prime t naught, here c1 c2, and here would be y naught prime. And there exists uniqueness of c1 c2 if the determinant of this coefficient matrix is not equal to 0. And obviously this determinant is actually Wronskian. We all of us know this is. Now I will see very useful theorem of Wronskian, Abel's theorem. This theorem is very important and very useful concept. And the statement of this theorem is, let y1 and y2 be two linearly independent solutions of second order homogeneous differential equation y double prime plus p2 y pt y prime plus qty equal to 0 on an open interval I. Then Wronskian of y1 comma y2 on I is given by Wronskian y1 comma y2 t equal to c e to the power minus pt dt. And this is true for some c who is depending on y1 and y2 but independent on t or on the interval I. This is actual theorem. This is the Abel's theorem, and the proof is such type. Since y1 and y2 are solution of this homogeneous second order linear equation, then y double prime 1 plus pt y1 plus qt y1 equal to 0. Consider this is equation 1. And second, y2 double prime plus pt y2 plus qt y2 equal to 0. This is noted as 2. Now multiply equation 1 by minus y2 and multiply equation 2 by plus y1. Then I will get y1 y2 double prime minus y1 double prime y2 plus pt y1 y2 prime minus y1 prime y2 equal to 0. I will get this equation, and we all of us know Wronskian of y1 equal to y1 y2 prime minus y1 prime y2. Then obviously Wronskian prime y1 y2 would be y1 y2 double prime minus y1 double prime y2. That means this equation would be reduces. If we put the value, then this would be Wronskian prime plus pt Wronskian equal to 0. Obviously this is first order linear equation. Okay. Therefore, by this equation, I will get the solution is such type. This value would be c e to the power integration minus pt dt. I hope my all viewers have understood this type of question. Okay, well. And we all of us know Wronskian is either identically equal to 0 or not equal to 0. If Wronskian is identically equal to 0, since e to the power minus pt never can be 0, so that implies c equal to 0. That means when the solution are linearly dependent, then by Abel's theorem, I will get constant c equal to 0. And when the solution is linearly independent, obviously Wronskian of y1 comma y2 not equal to 0. And since Wronskian of y1 comma y2 not equal to 0, that imply obviously c not equal to 0. I hope my all viewers have understood the Abel's theorem and the properties of Abel's theorem. Okay? See one nice example of Abel's theorem. The question is y double prime. The given differential equation is y double prime minus 2xy prime plus 2y equal to 0. And if y1 and y2 are two solutions such that y1 0 equal to 0, y2 0 equal to, here 1. Y prime 0 equal to minus 1 and y2 prime 0 equal to plus 1. And here we have to find the Wronskian of y1, y2 at the point x equal to 2. For this, Wronskian of y1, y2 given at the point x equal to 0. Here just use we know the Wronskian method. y1 0, y2 0, y1 prime 0, y2 prime 0. And this value would be obviously 0, 1, minus 1, 1. So this value would be plus 1. But in the question about Wronskian of y1, y2 at the point x equal to. For this, I will use the Abel's theorem, because Abel's theorem tell Wronskian of y1 comma y2 equal to c e to the power minus px dx. Here p means obviously minus 2x. So this value would be c e to the power here minus px. E to the power integration 2x dx, and this value would be c integration e to the power 2x, means this integration value would be c e to the power 2x over 2. That means this value would be c e to the power x. I have to find Wronskian of y1, y2 at the point x equal to 2. For this, since by this condition I have got Wronskian of y1, y2 at the point x equal to 0 equal to 1. That means just put the value Wronskian of y1, y2 at the point x equal to 0. This value would be c e to the power 0, and this value is obviously 1, and that means I have got the value of constant c equal to 1. Now my question, Wronskian of y1, y2 at the point x equal to 2. That means Wronskian of y1 comma y2 at the point x equal to 2 would be the value of c equal to 1. Then this value would be square. So by Abel's theorem, I have got this type of Wronskian. We will see one similar type of solution of Abel's theorem. Here the question is, if y1 and y2 be the two solution of the equation t y double prime plus 2y prime plus t e to the power t y equal to 0, and given Wronskian of y1, y2 at the point 1 equal to 2, and we have to find Wronskian of y1, y2 at the point 5. Here obviously pt equal to 2 over 3. Then by Abel's theorem, we can tell Wronskian of y1 comma y2 at the point t equal to c to the power minus integration pt means here 2 over t dt, and this value equal to c e to the power minus 2 log t, and that means here the value is c t to the power minus 2, and given Wronskian of y1, y2 at the point 1 equal to 2. That means Wronskian of y1 comma y2 at the point x t equal to 1, the value is 2. See, here t equal to 1. That means here 2. That means the value of c is actually 2. Now we have to find Wronskian of y1 comma y2 at the point t equal to 5. Since here I have got c equal to 2, therefore at the point t equal to 5, the value would be 2, 5 to the power minus 2, that means 2, 1 over 25. Now I will see some important properties of Wronskian. If consider some second order differential equation. If Wronskian of x is equal to 0 for any x belongs to AB, that implies Wronskian x is identically 0 for all x belongs to AB. Option 2. If Wronskian x not equal to 0 for any x belongs to AB, that implies Wronskian of x not equal to 0 for all x belongs to AB. Option 3. If Wronskian x strictly greater than 0 for any x belongs to AB, that implies Wronskian x strictly greater than 0 for all x. And option 4. If Wronskian of x less than 0 for any x, that implies Wronskian of x is strictly less than 0 for any x. In Abel's theorem, such property also will be hold. We all of us know in Abel's theorem, Wronskian of x equal to a to the power integration minus px dx. then Wronskian is either identically 0 or it is never 0. And 1, if Wronskian x naught equal to 0 for some x naught, then that implies Wronskian of x equal to 0 for all x. And option 2, if Wronskian x naught not equal to 0 for some x naught, then that implies Wronskian of x not equal to 0 for all x. And if Wronskian of x naught is alpha, we have any value, and this depends on alpha. If alpha greater than 0, then Wronskian of x strictly greater than 0 for all x. And if alpha less than 0, then that implies Wronskian of x strictly less than 0 for all x. If alpha equal to 0, then Wronskian of x equal to 0 for all x. This is true because here Wronskian of x not equal to alpha. That means Wronskian of x naught would be capital A times e to the power minus some px whose value would be alpha. Then notice here given alpha greater than 0 at the point x naught. This is the multiple of constant a and e to the power minus px. And this point is always greater than 0, e to the power minus px. Then obviously the constant a obviously would be greater than 0. So that means since a greater than 0, that means for all other x, obviously Wronskian of x would be greater than 0 for all x. If at the point x naught, the value of Wronskian greater than 0, then this is true. Wronskian of x is greater than 0 for all other x. Second condition, Wronskian x naught equal to alpha, here given alpha less than 0. Since alpha less than 0, that means obviously since e to the power minus px always greater than term. So since alpha less than 0, that means obviously a would be less than 0 at the point x naught. That means for all other point Wronskian of x, since the constant term is less than 0, that means for all other point Wronskian would be less than 0 for all x. I hope my all viewers have understood this concept easily. Okay. And this property and the property of Wronskian actually same. Wronskian of y1 comma y2 equal to 0 means either this row equal to 0 or this column is equal to 0 or this second row equal to 0 or this second column equal to 0. None of them happen. Then obviously Wronskian of y1 comma y2 equal to 0. If I consider Wronskian of y1 y2 equal to obviously y1 y2 y1 prime y2 prime. If we consider first row equal to 0, then y1 x naught plus comma y2 x naught equal to 0. Okay, that means from this expression we can tell, means obviously the solution y1 and y2 have common zeros. And if y1 and y2 are linearly independent, that means they never have common zeros. I hope my all viewers have understood this concept. Now, if we consider second row equal to 0, that means y1 prime x naught equal to 0 and y2 prime x naught equal to 0. That means y1 y2 does not never have common extrema. If y1 y common extremum if y1 comma y2 are linearly independent. Also, if y1 prime x naught equal to 0 and y2 prime x naught equal to 0, that implies y1 comma y2 never maximum Second, y1, y2 have never minimum. Third, y1 never maximum and y2 never minimum. Fourth, y1 never maximum, never minimum, and y2 never maximum, because y1 prime x not equal to 0 and y2 prime x not equal to 0 cannot verify this point is maximum or minimum. When y double prime x not would be greater than 0, then this y1, then this would be minimum, and when y double prime x not less than 0, then this value would be maximum value. I hope my all viewers have understood. Now, if we consider first column equal to 0, that means y1 x naught equal to 0 and y1 prime x naught equal to 0. That means when they are linearly dependent, then y1 have repeated zeros. Means if y1, y2 are linearly independent, then that imply y1 cannot have repeated zeros. If also I will do zeros in second column, that means y2 x not equal to 0 and y2 prime x not equal to 0. That means if y1, y2 are linearly independent, then also y2 cannot have repeated zeros. Okay. Now I will see one question which depends on this concept. The question has come in CSR Net June 2011 exam. The question is, let y1, y2x be the fundamental solution to the differential equation d2y dx2 plus px dy dx plus qx y equal to 0, where the interval x lies from closed interval AB. Where obviously px and qx be the continuous function and x naught is a point in the open interval AB. Here notice y1, y2x be a fundamental set of solution. That means obviously these two solutions y1 and y2 are both linearly independent. Then the question, both y1x and y2x cannot have a local maximum at the point x naught. Option 2, both y1x and y2x cannot have a local minimum at the point x2. Obviously both options are true because the solutions are given linearly independent. Option 3, y1x cannot have a local maximum at the point x naught and y2x cannot have a local minimum at the point x naught simultaneously. Obviously third option also right option. And option 4 indicate both y1x and y2x cannot vanish at the point x equal to x naught simultaneously. Cannot vanish at the point x equal to x naught simultaneously means this does not have repeated 0. So option 4 also right option. I hope my all viewers have understood why this type of concept is actually very important for higher study and for competitive exam. Today I will stop here. In my next video, I will discuss some question of Wronskian which had come in different competitive exam. Actually, this concept of Wronskian is actually very important for higher study. positive always and don't forget to subscribe my channel for more videos. Thank you so much.